Okay. This is pre-8-5. We're going to do a little bit of review since we've been on spring break. Let's see if we can remember everything in chapter 5 we've been doing. So the first thing I want you to try is to evaluate y equals 1/9 times 3 to the x. Notice again that x is in the exponent. That's what's different about this chapter. Is x is in the exponent. So find the values of x is 1, x is 3, and x is 4, and put it into this function and see what you get for a coordinate, and then we're going to graph it and see, and hopefully you remember what these look like, but if not, it'll be a good reminder. And I'm going to get some more problems down. Let's see what we can remember. Okay, a little bit more to review. Remember the exponential functions that we set up, very, very basic. Invest $2,500 in an account paying 7.25% interest, compounded annually. What's the account balance after 6 years? See if you remember how to do that. And then these are just a little bit down here of review. Remember, as you're going into these, anything to the 0 power is 1. Anything to the 0 power is 1. And to change the sign of a negative exponent, change the location. Okay? And we'll go over these in just a moment. Okay, so I think everybody's had time to work on these. I'm going to go ahead and work through them really quickly so we can have more time for the lesson. So you all were asked to evaluate this exponential function for x's 1, 3, and 4. So let's start with 1. We've got 1/9 times 3 to the first. 3 to the first is 3, and 1/9 times 3 is 1/3. So when x is 1, y gives you 1/3. Okay, so 1/3 is about right there. Okay, then we put in 3. 1/9 times 3 to the third is going to be 1/9 times 3 cubed is 3 times 3 times 3, which is, good job. And 1/9 times 27 is 3. 9 goes into 27 3 times. So then you get 3, 3 as a point. And then when you put in 4, it's 1/9 times 3 to the fourth, which is 1/9 times 3 to the fourth is 3 times 3 times 3 times 3, which is 81. And then, again, I'm just assuming y'all remember this. 9 goes into 9 once, 9 goes into 89 9 times. So 1 times 9 gives you 9. So that's 4 comma 9. Kind of butchered it, but that's what it is. So 4, 4, 9 is up here. Okay, now I think you all are kind of seeing what's happening here, but just a reminder, you all, what is this value right here? When it's in the form y equals a times b raised to the x, it's your starting value and it's one other thing. Do you remember? It's your y-intercept. Good job. So 1/9 is your y-intercept, and it's really hard to draw this even closer to 0, but it's like right there at 1/9. So just a reminder, your x-axis is your asymptote, and this thing just starts shooting up really, really quickly. There's not supposed to be a lump there. I got off a little bit, but there you go. There's your graph. And if you wanted to confirm that, go to your y equals, and I've got it ready just for review's sake. And there you go. There's your graph. Okay, so we did it. Yay, good job. So let's move on. The exponential tends to go up really quick, or it tends to go down very quickly. I'm going to try to squeeze those in before we end chapter 8, but right now I kind of felt like we needed to get into this stuff more. So anyhow, let's move on to 2. When we got into this lesson, it was all about exponential growth. So it was still exponential stuff. When it came to the money, Y was your account balance. Your A is your starting value. So you all probably put 2,500 there. Okay, now, tell you what, I'm not going to say all of this. For your interest rate, it is moving this 2 to the left. So that is 0.0725. And since it was annual, 6 goes in for the exponent. Did I forget anything? Good job. Remember, with the exponential growth, you're adding it to the 100%. You've already got the money in there. So this is the interest that's added to it. So don't forget to add it to 1. Okay. And once you put that in there, did you all get $3,804.73. Yes. Okay. So if you got that, good job. Now these should fly by. Let me make sure I'm recording. Okay. 7.25 to the 0 power is 1. Okay. Now watch these and be careful. I'm going to skip over to number 5 for a minute. See how the whole thing, -5 is in parentheses and it's raised to the 0 power. So this is 1. But this is actually the opposite or the negative of 5 to the 0. So what is 5 to the 0? 1. And then the opposite of that is -1. So just be careful on those. So many people still miss those. Okay, reminder on this. We've got 7 raised to the -1. Yeah, generally we don't like negative exponents. So think of 7 as being over 1. And to change the sign of the exponent, we're going to change location. So that becomes 7 to the +1. And there's nothing else left up here, so it's understood to be 1. So if you got 1/7, because 7 to the first power is 7, so if you got 1/7, good job. Okay, now let's move on to this one. Again, think of -4 raised to the -2 as being over 1. We want to change the sign of the exponent. We're not really worried about the number, just the exponent. So to change that sign, -4 moves to the denominator and -2 becomes +2. Is there anything left in the numerator? No. So it's just really understood to be 1. And so then simplify that more. 1 over, what is -4 when we square it? Yeah, +16. -4 times -4 is +16. So if you got 1/16 for that, muy bien. Good job. Okay, now this gets a little hairy, but not bad. Kind of take note. The instructions for problems like this were to write this with positive exponents. J to the 4th is already positive. -2, that's just an integer. It's not a negative exponent, so we don't have to worry about it. So it looks like the only two that we have to move are these two, okay? So keep the -2 where it's at, keep the j to the 4 where it's at, and h to the -7 comes up to be h to the +7, and k to the -3, it goes down and becomes k to the +3. I hope I said that right. I think I wrote it correctly. Y'all agree? Okay, is that coming back from over a week ago? No? Mm-hmm. Over j to the 4th, k to the 3rd. And notice all the negative exponents are gone. They're all positive now, and that's happy times. Yay. Okay, y'all ready? Let's do some maybe new stuff. Okay, in code, if you have done scientific notation before, give me a thumbs up. If you have not, thumbs down.
You know what? I remember the name. I don't remember how to do it.
Okay. Okay, okay.
700. It would be the 1.7 and then like the power of
Yeah, you can help everybody else. We'll need you. It's okay. We got this. I said, y'all, I'm such a goof. I said this is pre-8.5. It's actually 8.4. My bad. I'm wanting to kind of skip stuff. I'm skipping 8.3 temporarily. I want to come back to it, but I don't want to skip 8.4 right now. So fix that. My bad. Okay. I'm going to be honest, I like this book and this material, but this is one chapter where I kind of feel like they must have been getting tired, or those interns were just really not doing what they were supposed to be doing. So the next few sections, in my opinion, kind of all blur together. So just ask lots of questions and I'll try to keep it straight for you. Scientific notation is essentially this. It's where you've got a number, a times 10 to the n, where n is an integer. And I'll be honest, I never could used to remember that. An integer is like the whole numbers, 0, 1, 2, 3, so on and so forth, and their opposites, -1, -2, etc. So basically, no decimals in this, no fractions. You want whole numbers and their opposites. Okay, and the absolute value of A must be less than 10, but greater than or equal to 1. That's what it's going to look like. A times 10 to the something, where n is an integer, and the absolute value of A must be less than 10, but greater than or equal to 1. Little things to note about this. If n is positive, we'll just say indicates large number. If n is negative, indicates small number. Okay, I'm going to try to write bigger, you all. My bad. If n is positive, that indicates large number. If that exponent is negative, that indicates a small number. You try this? Okay, now there seems to be a lot of review in here and a lot of stuff thrown at you, so I'm just going to give you chunks of it, okay, and see if it makes sense. So the first part is if I give you something like this, 10 cubed times 10, we'll say to the second, okay? The rough way to do this, the hard way, is 10 cubed, you all know, means 10 times 10 times 10, right? And 10 squared means 10 times 10. Agreed? Okay, so how many 10s do we have being multiplied by each other now? 5. Do you all see an easier way that we could have gotten to that? You got it. Just add the exponents. So when you see powers being multiplied and they have the same base, just add the exponent. So to drive that home for just a little bit, if we have 10 to the third times 10 to the first, what is it? 10 to the 3 plus 1? Yeah, 10 to the fourth. Okay, I'm writing too small again. Oh, sorry. Yeah, 10 to the 3/3 power. Yeah, it would have been 1/3. I see what you're saying though. Okay, now they're not going to all be that easy when we hit them. I don't know why I'm hooked on threes today. 10 to the -3 times 10 to the fifth. Again, same power, same base. They're being multiplied. What do we do with the exponents? Add them. So what's -3 plus 5?
2.
Yeah, so that would be 10 squared. Okay, one more of these. Let's say you have 10 to the first. If there's no number there, it's understood to be 1, times 10 to the -2. Again, they're being multiplied. The base is the same. So what do you do with the exponents? Add. So 1 plus -2 is, there you go. Keep forgetting to put the base. 10 to the -1. I wrote that all wrong, but you know that's 10 to the -1. Okay, so if multiplying powers with same base, add exponents. And again, they throw that into this lesson. We actually learn that the next lesson. So if you can get it with the power of 10, then like the next thing that we do is going to be crazy easy because you'll know to apply that to X's and 2's and Y's and whatever, okay? So if you're multiplying powers with the same base, in this lesson, they're all going to be 10s, add the exponents. Good on that? Okay, again, not crazy exciting stuff, but guess what? Let's go the other way, just so you're not surprised. Let's say I've got 10 times 10 times 10 times 10 divided by 10 times 10 times 10. Okay, now, shorthand. What is 10 multiplied by itself 4 times? 10 to the fourth, right? And 10 multiplied by itself 3 times, you got it, 10 cubed. Okay, now look at this. We know 10 divided by 10 is 1, 10 divided by 10 is 1, 10 divided by 10 is 1. What is your final answer? 10, right? What would be an easier way to do that? Subtract the exponents. So good job, if you all are dividing by the same base. You're dealing with powers. You're dividing by the same base. Subtract the exponents. 4 minus 3. And I should have written it up there. It's 4 minus 3 is 10 to the 1. And just a reminder, 10 to the 1 is 10. We don't typically write to the first power. Okay, so does that make sense? Okay, and again, if you can get it with tens, it's going to make the next lesson really easy if we can just get through today. Okay, we'll do one more of those just to drive home the point. Let's say you've got 10 to the 12th divided by 10 to the 7. My first thought is, man, 7's not going to go into 12 evenly. But do I even need to do that? No, we're dividing powers, and exponents have their own rules. When you're dividing, they have the same base. What do you do with the exponents? Good. So this is 12 minus 7. This is 10 to the 5th. Yes, you can.
So do you always just try to make a positive number, or is it?
No, you could get like 10 to the 11th over 10 to the 20th. Yes, you could, since you see this is going to give you a -9, you could go, wait, where are there more 10s? Yeah, so you could do 20 divided by 11, and that's going to give you 10 to the 9, and then keep the 1 in the top. You could do that. 20 minus 11 is 9. So if you go this direction, 20 minus 11, that's going to stay in the denominator.
You can also say 10 to the negative.
You could do 11 minus 20 and get 10 to the -9. But then when you want to get rid of that negative exponent, it kicks it down to the denominator anyway. So you're going to wind up there eventually. So it's however you want to think about it. But I don't think we're going to get that complicated today. Mainly just be able to do this top one. Okay. Y'all good so far? Okay. Kind of slap yourselves, cold water on the face. Now we're going to get into the scientific notation. Actually, a little bit more review. Because if I'm losing you on this stuff, then the scientific notation part is going to be extra confusing. Okay. Little bit of a reminder. I think they throw this at you just to make sure you're remembering everything. Let's say you got a number. This is your decimal part. What place is this? Yep. Here's your ones. Then your tens, then hundreds, then thousands, right? Again, just kind of dusting out some cobwebs. Then what's after that? 10,000s. You got it. And then 100,000s. Good job. 100,000s. I need sharper markers. And let's go ahead and here. Every 3, remember there's a comma. Boom, comma. And after the 100,000s, what do you hit? Millions. Good job. And then it goes from there. Your 10 millions, your 100 millions, then you hit billions, then 10 billions, 100 billions, then you hit. Yeah, trillions. It gets, yuck. Now, if I had money, I'd want the trillions, but right now our nation is in debt that much, so it's kind of sad. But anyhow, so there's that review. And then let me just remind you that for millions, how many zeros are there? So like if we had 6 million, 6 zeros. And then if you have billions, how many zeros?
7.
9. And you can get this one. How many for trillions? It's 3 every time. 3 every time.
Oh, this is making sense now.
12. Okay, so just if that helps anybody, and while we're at it, because the thing about scientific notation is it is helpful for really big numbers and really small numbers. And so that's why we're doing a little bit of this review, okay? Just trying to dust out the old cobwebs. So really before, let me go ahead. We'll get to those in a minute. So let's say I ask you to write some in scientific notation. This is example 1. Okay. And I tell you, this is the distance from the sun. It is 93. You may get some things like 93 million. So this is where it's helpful to kind of know your zeros. So for 93 million, that's 93 plus 6 zeros. Remember doing that?
Yes.
Okay. So if not, though, that's why I'm giving you this information to make it a little bit easier. But okay, that's lovely. We rewrote it with zeros, but they still want it in scientific notation. So let me stress this. Again, scientific notation, the absolute value, the number has to be less than 10, but greater than or equal to 1. So come back over. If I put the decimal here, I'm at 93. You know what? I'm going to skip just a little bit. I'm going to come back. Hang on. A little bit below. I missed this. I forgot to do it. So here's your game show. Is this in scientific notation or not? Number 1, let's say you have 2.004 times 10 to the negative 23. Class, is this in scientific notation?
Yes.
Yes, because this is less than 10, but greater than or equal to 1. So it's 2.004. So that's okay. Times 10 raised to an integer, negative 23 works. So this is actually a yes. This is in scientific notation. Yes.
Yeah.
No, you'd have to fix it. And the reason we are like, I may have to act some things as we get closer to summer, but scientific notation comes up in science classes. And so I kind of feel like y'all have to be pretty solid in that. So we will practice this a lot the rest of the year, I hope. Okay, number 2. Good question, Isaac. What if I give you negative 12 times 10 to the negative 2? Is that in scientific notation or not? Right, because the absolute value of negative 12 is greater than 10. So that's a no-no. We would have to fix that, and we'll work on that in a minute. Number 3, and if you want for your notes, you can put absolute value of negative 12 is greater than 10. So that's what knocks it out. Okay. 3, what if I give you negative 1.2 times 10 to the negative 2? Is this one in scientific notation or not?
Yes.
Yes. Okay.
Yes. Yes.
Yeah, it is. The absolute value of negative 1.2 is greater than or equal to 1, but less than 10. So this one actually is okay. Yeah, no, you're good. You're good. And our times 10 to the negative 2, that's fine. Then number 4, what if I gave you 11.0 times 10 to the 4? Scientific notation or not? No. Why not, Travis?
Because 11 is bigger than 10.
You got it. You got it. That's the problem. 11 is greater than 10. That's what knocks it out. So that's a no. Okay. So just kind of making sure you know how to spot what's appropriate and what's not. Y'all good on that, or do I need to explain it a little bit better? Good question. Okay. If you have, I'm trying to think if I should get into that. 10 times 10 to the 5th would not work because this has to be, look at your definition, it has to be less than 10. Yeah, and I can explain, I'll explain in a minute how to fix that if you get it, okay? But for right now, let's work on these and get you warmed up. We want this, go back to example 1A. We want this in scientific notation. It's too big, it's icky, we don't like it. So we got to think, where do you want to put that decimal so that it's less than 10, greater than or equal to 1? You got it. We're aiming here. 9.3 is less than 10, but greater than 1. So start here and count over 1, 2, 3, 4, 5, 6, 7. So it's going to be 9.3 times 10 to the 7. Big numbers are going to have a positive exponent. Okay. Y'all back me up. Is that 7? And if it helps, like every comma is going to be 3. So 3, 6, 7 can be a quicker way to count. You good on that? 9.3 times 10 to the 7th? No, y'all help each other if I'm not saying it well. Okay. Let me skip over to the next one. Okay, before I get into the next one, let's do a little bit more review. No, I'm sorry. I am all over the place with my decisions. Let's talk about, I want you to try this one. What if you find out that our national debt is $31.4 trillion? I think it is. Doesn't that stress you out? It stresses me out. Okay. Oh.
Yeah, man.
I can't sleep at night if I watch that stuff. I have to pray. Okay, so this is where it may be helpful. Trillions, I told you earlier, that's 12 zeros. So one way you could do this is do 1 trillion is 12 zeros. One way to think about it, okay? I think we could probably go to scientific notation pretty easily. But then when you think about this many zeros for trillions, that decimal is going to land right where the comma is. So this would be, I'm trying not to skip steps, 31.4 trillion. See what we did there? The 31.4 goes right over the comma. And now kind of think, let me ask you this. Where does the decimal need to land now to be between 1 and 10? You got it. So we're aiming to put it here. Okay. So starting here, you know your decimal is here. 3, 6, 9, 12, and then we go over to 13. So this is going to be 3.14 times 10 to the 13. Oh, yeah. Perfect. I actually didn't plan that. So, but hey, if that stresses you out, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that's another way to represent our national debt. Yay. Feel free to go into politics and help clean up this stuff, y'all. I'll vote for you. Okay. Yeah, it's tempting. Okay. Okay. I don't know how far I need to go. Let's review this side so that you're comfortable with your decimals. Now, notice this time, we're going small numbers. Scientific notation represents big numbers really well and small numbers really well. So looking at your decimal, what is this first place? Yep. And don't forget, look for the ths on them so it keeps you straight, okay? Tenths. And then we've got hundreds. Good job. And then, there you go. I'm really bad at it, so I'm glad you got it. Tenths, hundredths, thousandths. I'm butchering it. God bless y'all. You can do this. And then your 10,000ths. So just really the reminder there, look again for the THs. What's after 10,000ths? Yep. Good question. No. 100,000ths. And then, is it millionths? It just doesn't even look right. Millionths, and then the 10 millionths, and so on. Okay.
Spelling someone, that means there are 2 ways for them to correctly spell this. And spelling book will probably do one of them.
I don't know. Just be careful.
Not things done, but
Wait, what? Okay, anyhow. Okay.
So it's like the syllables are shorter, so you say, why have to do the 1/1000 for this thing?
Okay, classroom discussion. Let's keep going. Now, this one doesn't incorporate this, but let's go ahead. Decimal, this is a really small number. Think, and I know I've kind of spaced them out and I shouldn't do that, but to kind of help it to be easier to see where the zeros are, just letting you know. We want the decimal to land right here between 5 and 2, so it's 5.2. Again, so the absolute value of A is less than 10, but greater than or equal to 1. 5.2 will fit that bill. So do 5.2 times 10 to the, now count it over, 1, 2, 1, 2, 3, 4, 5, 6. And what I leave off needs to be negative. The -6 indicates it's a small number. Okay. Are y'all good with this so far? Have y'all done this and you just kind of forgot, or is this?
Yeah.
Okay, some of y'all, this is brand new. So stop me when I'm losing you. Okay, I'm trying to make this make sense. D, now 1095 millionths. I think I said that right. They want you to put that in scientific notation. Okay, so I'm trying to think of the easiest way to show y'all to do this. You've got your decimal, and you might even want to just do the slashes. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. And then once you've got that, put in the 5, the 9, the 0, the 1, and then for the rest, put in your zeros. Okay, you all may have had teachers that taught you a different way, a better way. That's fine. Do it that way, but if nothing else, maybe that will get you. Okay, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. Put the little dashes and then put your number in and fill the rest in with zeros. Once you've got that, now let's take it to scientific notation. Where do I put that decimal? Good job. I heard Isaac say it. Nice job. We're aiming for that. So let's go ahead and do the 1.095 times 10 to the, now be careful counting over, 1, 2, 3. And because it's a decimal, it's a small number, we put a -3. Okay, still good? Aren't these fun? Okay, indifferent. New stuff is usually not fun, but I think you'll like it once you get used to it. Okay, can I keep going? Say what? Right now, you're not grabbing these. Okay. Okay. 25 hundredths. Again, notice the TH, the th. So this is going to be a decimal. So do your decimal, your 0, and then tenths, hundredths, tenths, hundredths. Okay, so there's only 2 places there. Put your 25 in, and now you're ready to take this to scientific notation. What do you think? Where's it go? Yep, 2.5. We want it right there. 2.5, because that's less than 10, but greater than or equal to 1, times 10 to the, now we go 1 space over. And since this is a decimal, make it -1. Okay?
You don't show the exponent 1.
Yep.
Like, do you only ever show it when it's a -1? Right, you just like, or do you just not throw it and just like, it would just be imaginary?
Well, everything,
Or would
like,
you
you could
say
say
it's-
2 plus 5, and it's just 2 power of 1 plus 5. It's like saying 1.0000000. And you can write infinite number of zeros, and you can always put 2 power of 1, but it's still the same number. It's not changing.
But if it's a negative,
It's
I don't know.
negative.
I will say on this, I can see why they put the 1, because part of me wants to go, well, is that supposed to be a fraction? Is this 10 raised to the 1/3? Or is this, so I don't know. For some reason, mathematicians say that we should put the 1 in that case. But good question. Good question. Okay, now, y'all, I think we can handle this. Let's say we have 83.7 times 10 to the negative 4. Okay. What is the problem with this, Julie? You got 83.7 is greater than 10. So we've got to fix this. There's a couple of ways you can tackle this. One is to rewrite this in scientific notation. Take that decimal and we're going to move it over and write it as 8.37. Y'all agree that's less than 10 but greater than or equal to 1? Okay. Now, 83 bigger than 0, so we're going to write that as 10 to the, wait, how many spaces did I move it? 1. So 10 to the 1. Okay. Now, bring down the rest of it times 10 to the negative 4. And you'll see why we did that little review or practice at the beginning. Keep your 8.37 and now focus on these. What is 10 to the first times 10 to the negative 4? We are multiplying, so we add the exponents. So if you said times 10 to the negative 3, you are correct. Good. This is one place it comes in handy. Okay. Now, another way to think about this, I'll try to use a different color. Okay. See how 83.7 went to 8.37. Going from here to here, did it get bigger or smaller? From here to here. Smaller. So to counter that, this side has to get bigger. So let me put this one went smaller. So to balance it, this side needs to get bigger. And if you're on a number line, when you move from negative 4 up 1 to negative 3, that's getting bigger, correct? Okay, so you could think about that. Take this one place.
Could you also just do the opposite of what's being done? Like, couldn't you move it 4 over to the left, the decimal point, and then just like redo it and put it back?
Oh, you could.
That's what I was
Yeah,
like.
yeah. You could do that. And I'm fine with that. I'm just saying this might be quicker once you get used to it, but that would also work. Okay, so let's do a couple more of those. 165 times 10 to the third. Again, I think you're realizing 165 is greater than 10. That's our problem. So I'm going to cover this up for a minute and let's rewrite 165 in scientific notation. The decimal needs to go right here, becomes 1.65 times 10 to the, now think, decimals here, 1, 2. So it's 1.65 times 10 squared. Now, let me put that in parentheses. Don't forget about your times 10 cubed. And so now let's wrap this up. It is, am I going too fast, y'all? Okay, 1.65 times 10 to the, what's 10 squared times 10 cubed? There you go. Okay. The other way, if you want to think of it as bigger and smaller, 165 went to 1.65. So it went 2 places smaller. This side goes 2 places bigger. So it balances out. Another way, or the other way that you're talking about. Let's do one more of these and then we're going to switch it. 0.095 times 10 to the negative 1. What's the problem with this? Yeah, it's too small, okay? We need it to be greater than or equal to 1. So we are aiming, I think you all can see this now, we need to put the decimal right there at 9.5. So again, go ahead. If you think you know it, you can do it without watching me. Rewrite this part as 9.5 times 10 to the, and again, I'm going 2 places here, 1, 2. And since it's a decimal, it's 10 to the negative 2. And then don't forget about your times 10 to the negative 1. Wrap this up. We have 9.5 times 10 to the negative 3. Negative 2 plus negative 1 is negative 3. Okay. That's all example 1. Hanging in there okay? Okay. Yeah, we might have to get some study groups and help each other. But again, if nothing else, I'm aiming for y'all to be exposed to it. Now you're going to have some that say write in standard notation. Y'all, that's how we normally write a number, okay? So if you have something like 8 times 10 to the 5th, Since this is a positive exponent, is this a small number or a big number?
Big, no.
Big number. When it's positive, it's a big number. So get your 8. Your decimal's understood to be there. And since it's 5, you're going to go 5 to the right to make it a big number. So 1, 2, 3, 4, 5. Land your decimal and then fill in all those zeros.
Didn't technically just put 5 zeros.
Yeah. In this case, you could. Absolutely. Well, when you get like 8.273, it may be helpful to do that way. But yeah, good question. And so put your comma in there. And this is 800,000 to make it nice and neat. Oh, did I? Sorry. GHI. Oh, good job. Y'all are still awake. That's exactly how I planned it. Okay. And then K, I think we're almost to the end of example 1. 7.1 times 10 to the negative 4. Notice your exponent. It's negative. So we want to go left to make a smaller number. So, yeah, I should have given myself more room. Hold on. If you think you know it, go ahead and do it. 7.1 to make it smaller, go left. So 1, 2, 3, 4. Land your decimal and add in those zeros. And so now it's 0.00071. Right there. So positive means go big. Go to the right in this case. And then negative means go small. Sorry, if you're, depending on which way you're converting determines whether you go left or right. So that's why I'm just kind of avoiding the left or right. Think big or small and you'll know which direction, where to go. Okay, y'all are doing awesome. Can I keep going? Okay, actually, let me flip this. Example 2. You may have some like this. Did I mess it up again? I don't care. Y'all know your alphabet, fill it in appropriately. My alphabet is not my strong point. Okay, let's say you're asked to simplify something like this. 7.5 times 10 to the negative 4. This scientific notation divided by 5. It's all a matter of kind of like terms. You're going to take the integer and divide it by the integer. So what is 7.5 divided by 5? You want to put it in your calculators, do it by hand. It gives you 1.5. Then bring down your times 10 to the negative 4. You may get some as easy as that. Understand that one?
It's divide 7.5 by 5.
Gives you 1.5, then bring down your 10 to the negative 4.
And just forget about the negative.
Yeah, this is in scientific notation, so you can stop. You didn't have to do anything with the exponent there. Good? Okay. B, now you know they're not going to stay that easy. But you all can handle them. Okay. Again, kind of like looking for your like terms. Your 4 and your 3, they're just your regular old integers. So multiply those. 4 times 3 is 12 times 10 to the 5th. Can I leave my answer like that? No, Travis, because the 12 is? Yep, that's our problem. It's bigger than 10. Good job. So again, use one of those techniques that you did before. Go big or smaller. Or you can write 12 as 1.2 times 10 to the what? Decimals here, it moved over 1, so 10 to the 1. 1.2 times 10 to the 1 times 10 to the 5th. And your final answer is keep your 1.2 and 10 to the 1st times 10 to the 5th is 10 to the 6th. Good job. Y'all have caught on to that very quickly. Okay, so just check your final answer to make sure it's an appropriate scientific notation. We're actually about to wrap this up. Y'all are doing awesome. 3 times 6.1 times 10 to the negative 3. Take a minute and see if you can do that. Go solo. Y'all got this. Okay, I'm gonna jump in because of lack of time. If you did 3 times 6.1, I don't trust myself right now. I'm not even doing my alphabet right. 6.1 times 3, and you get 18.3 times 10 to the negative 3. You would get partial credit for that on a test, but the problem is the 18.3 is greater than 10. So rewrite that as, or however you convert it, okay? But that becomes, move it there, 1.83 times 10 to the 1. And then we've got our times 10 to the negative 3. So for the big finale, keep your 1.83 and add those exponents. 1 plus a negative 3, negative 2. So if you got 1.83 times 10 to the negative 2, pat yourselves on the back. You're doing great. And hang in there, y'all. We are almost done. I think I'm going to go ahead. Example 3. You have 2 more, and I'm going to give you your homework, and you can run from here. Round to the hundredths place. Because I really think y'all are getting it. I'm so proud of y'all. Round to the hundredths place. So for this one, let's say you have one like 3.11 times 10 to the negative 2 times 2.7 times 10 to the negative 4. Kind of like the like terms again. You know you're multiplying. 3.11 times 2.7. Multiply those. You get 8.397. I'll just save you the time. And now look at this. I'll do those in squiggly. What is 10 to the negative 2, bless you, times 10 to the negative 4? Remember, when you're multiplying powers, you add the exponent. So I think I heard it, times 10 to the negative 6. Negative 2 plus negative 4 is negative 6. Is this one good in terms of scientific notation? Yes. Okay. That 8.3 is less than 10, greater than or equal to 1. The only problem is we need to round to the hundredths place. So that's tenths, hundredths. The 7 pushes that to, well, 0. 39 becomes 40. So 8.40 times 10 to the negative 6, and you would have that answer perfect. Okay. One more. One more. Let's say you have something like 2.9 times 10 to the negative 10 over 7.85 times 10 to the negative 15. There are several ways we can tackle this. That's okay. I'll stick to one method for now. Okay. Again, do you see this is division? 2.9 divided by 7.85. Anybody can put that on the calculator, so I'll just go ahead and do it. 0.3694 times. Now, since this is multiplication, we could officially flip those and make this 10 to the 15 over 10 to the 10. Okay, to make positive exponents. Or we could just do 10 to the negative 10. Oh, wait, remind me, when we're dividing powers, you got it, we subtract. Negative 10 minus negative 15, again, be careful, becomes 10 to the negative 10 plus 15. So it's 10 to the 5th. Okay, now that's great. You get partial credit if you got that far. Problem. It's got to be greater than or equal to 1, so this is too small. So we are going to move this over 1 and make this 3.694 times 10 to the, what was it? Oh, wait, you're jumping ahead of me. Let's keep it focused just on this right now. This is 10 to the negative 1, okay, because it's a decimal. Now bring down, yeah, Isaac, you're doing great. You're just working ahead in your brain. Bring down your 10 to the 5th. And so we have 3.694 times 10 to the, now we're multiplying powers, so we add. Negative 1 plus 5 is 4. Yeah. If you can go from there to there, I think I know what you're doing. Okay, and then the last thing is we want it to the hundredths place. So that 4 does nothing to the 9. So it's just 3.69 times 10 to the 4th. Okay. Y'all, here's your homework for Monday and Tuesday. Just go ahead in your workbook, practice 8-5 example. Do numbers 1 through 54 all. Just do the whole page, go straight through. And I think I have gotten a little bit of everything to help you. So you can do it. Please don't put it off to the last minute. While it's fresh in your brain, do what you can. Okay. And then if we need to pick back up on this Thursday, just let me know. And I'll see you Wednesday. Don't forget Pi Day on Wednesday. Bye.